When you introduce a high-volume input into a rigid, narrow distribution channel, the result is predictable. You get a violent backlog. Modern engineering teams are currently experiencing this exact physical reality in their software delivery pipelines. AI coding agents can write code roughly 10 times faster than a human engineer. Yet across the industry, engineering productivity has scaled by approximately 20%, not 200. Engineers actually spend a fraction of their day typing syntax. The remaining 60 to 70% of their time is absorbed by necessary operational friction, such as complex deployments, endless sprint planning, and most crucially, code review. This diagram illustrates the disconnect. The code generation phase expands by an order of magnitude, but the human review node remains dangerously constricted. The sheer volume of output forces the issue. Engineers do not have the bandwidth to audit these diffs. Either the pull request rots in the queue for days, entirely negating the speed advantage of using AI, or the reviewer rapidly scans the code and rubber stamps the approval to keep the sprint moving. The AI productivity paradox exists because traditional human code review was not designed to scale as the primary quality gate in an AI-accelerated pipeline. Resolving the paradox requires moving those approval gates upstream. When an engineering team rubber stamps AI-generated code to maintain velocity, they are quietly accumulating a highly specific, rapidly compounding form of technical debt known as AI code slop. Slop is dangerous precisely because it easily passes the rapid eye test of an overwhelmed reviewer. It compiles without errors, it passes basic linting checks, it utilizes recognizable production-hardened syntax. The logic looks plausible, but it is subtly and structurally wrong for the specific system it lives in. Consider convention blindness. AI models generate excellent generic code, but they are often blind to a specific repository's unwritten rules. An LLM will reliably ignore established naming conventions, bypass preferred logging patterns, and violate strict module boundaries simply because those constraints were never articulated in the prompt. Then there is defensive overreach. LLMs are heavily trained to handle failures gracefully. In practice, this often translates to excessive try-catch blocks and redundant error absorption. The code silently swallows exceptions instead of surfacing them, effectively destroying observability and making future debugging nearly impossible. AI also frequently engages in cargo culting, applying massive enterprise patterns to simple problems. Asked to solve a local issue requiring 15 lines of logic, a model might construct a 200-line abstraction layer featuring retry logic and circuit breakers for synchronous calls, where retries make no sense. Standard automated testing pipelines are often blind to these specific failure modes. While a test can verify if a function returns the correct string, it rarely flags whether that function uses 20 unnecessary lines of abstraction or violates a team-specific logging pattern. Tests verify behavior within the scope of what the author thought to test. If an engineer had anticipated the subtle logic failures introduced by the AI, they would have specified them in the original prompt. To isolate the exact mechanism that generates slop, we have to look closely at the information disparity between a human-generated pull request and an AI-generated one at the moment it reaches the reviewer. Observe the human workflow on the left. Intent travels with the author into review. But in the AI workflow on the right, specific intent is abandoned in a chat prompt. The syntax is preserved, but the architectural reasoning vanishes. Deprived of explicit intent, human reviewers are severely handicapped. They cannot definitively judge if a complex abstraction is genuinely correct for the system architecture. They can only confirm whether the syntax is valid. Eliminating AI slop requires a structural change. Engineering teams must review the architectural intent of the code before the LLM generates a single line of syntax. The software development platform Aviator ran an experiment to test exactly what happens when you formalize intent upstream. They tasked a team with building a complex hierarchical configuration system with a strict constraint: 0 manually written application code. The scope included database models, a resolution engine, a complete GraphQL API, and a front-end settings interface. Done conventionally, this would trigger dozens of iterative review comments across multiple PRs. The team began by restructuring the workflow. Instead of jumping to code generation, they fed a scaffolding product requirements document to an LLM agent,
prompting it to ask clarifying questions and collaboratively generate a strict, comprehensive technical specification. This diagram maps the new workflow.
Engineers bypass downstream code review, redirecting their labor upstream to the generated specification. This deep review locked in implementation constraints, mandating specific UI component choices, validation requirements, and caching strategies. The second layer audited scope completeness. The human engineers caught missing user experience requirements and flagged architectural hallucinations, such as the spec referencing a database table that did not exist in their system. Catching an architectural error at the spec stage requires a sentence. Catching that identical error post-implementation requires discarding the code and starting over. By utilizing AI to write a rigorous specification, the team formalized their intent, replacing fragile human context with explicit, machine-readable rules for the implementation. With the intent locked, the generation phase began. An AI agent took this final spec, 14 acceptance criteria containing 65 checkable items, and autonomously generated 6,000 lines of code across 4 distinct execution phases. Without any explicit human instruction to do so in the prompt, the implementation agent strategically chose to write its own comprehensive test suite to verify it met the 65 acceptance criteria. Once the code was pushed, a secondary, independent AI agent performed the verification. This agent tested the generated pull requests strictly and exclusively against the 65 approved specification items. The speed differential in this phase dictates the success of the model. While the human team spent 10 hours meticulously reviewing the intent, the secondary AI agent generated a highly structured verification report in exactly 6 minutes. When humans finally did scan the implementation, the remaining code review was downgraded to catching minor convention-level issues: import placement, enum duplication, and stale editor states. Moving the approval gate separated the review process into its optimal components. Spec review catches catastrophic design failures before they are built. Code review is appropriately limited to catching superficial syntax conventions. The Aviator experiment proves that front-loading human effort into verifying the intent allows AI generation throughput to scale rapidly without compounding technical debt. Transitioning a team to an intent-driven pipeline typically triggers immediate resistance from senior engineers. The primary pushback is that writing rigorous specifications feels like a return to slow, heavy administrative overhead. That objection is valid in a human-only workflow, but it ignores the tooling. AI eliminates administrative overhead by generating the structured specifications itself from a brief set of human requirements. Implementing this workflow requires 3 immediate interventions. The first is scoping AI tasks tightly. Teams must stop using open-ended, monolithic prompts like "build this feature." Massive, unstructured prompts afford the LLM too much latitude, reliably producing high volumes of code slop. Decomposing large features into explicit subtasks with constrained boundaries improves the quality of the output and simplifies verification. The second intervention is mandating that intent becomes a first-class artifact in your pipeline. Documenting the overarching reasoning must become a required step before any code is generated. This feedback loop shows the mechanics. You just need a minimum viable spec, 2 to 3 simple sentences defining the scope, a generated list of testable acceptance criteria, and a strict note detailing what is structurally out of bounds. The third intervention is actively moving the approval gate. For any AI-assisted task above a defined complexity threshold, mandate absolute human spec approval before an engineer is permitted to initiate LLM implementation. Establishing this pipeline forces developers to document the what before generating the how, ensuring the implementation remains anchored to the original design. The final operational tool required to stabilize this pipeline long-term is building and maintaining a team Slop register. Every codebase contains idiosyncrasies that generic LLM models consistently fail to grasp. The Slop register tracks the specific error-handling conventions and module boundaries the AI repeatedly hallucinates. You operationalize this data through a feedback loop. Feeding it backward into base prompts prevents known slop, while feeding it forward into CI checks catches residual drift immediately. By integrating the Slop register, you create an AI-native system that continually hardens itself against LLM hallucination drift, rather than relying on the endless vigilance of human code reviewers. AI will continue to accelerate the sheer volume of code written.
Engineering leadership is no longer about managing that output. It is about architecting delivery pipelines rigorous enough to explicitly define the intent the AI must follow.